Hey, AP Chemsters, this is Mrs. Vanderlei bringing you another Blankwalle video. This is 7.3. So we are just following 7.2, where we learned about the nature of light. And we learned that light has wavelengths and light has frequency. And then with Max Planck's help, we learned that light has energy. And he's the one that came up with the direct relationship between energy and frequency, which means the indirect relationship between frequency, energy, and then wavelength. So as wavelength goes up, frequency and energy decreases. And there are equations in which we learned in 7.2 that you can calculate each one of those. As the wavelength decreases, then again, frequency and energy increases, okay? We learned that violet is the greatest energy and the lowest wavelength of all visible light. And we learned that, let's say UV has the greater energy between that and visible and IR. Okay, so we learned some relationships there, okay? Well, how does this help us? Well, we need those relationships to further understand the new model, the Bohr model of the atom, okay? So this is going to relate to how we understand the atom. So Bohr used hydrogen atom, okay? And when is a sample of hydrogen gas is given energy, all right? Well, how do they do that? Well, we do it by adding energy, usually in the form of, come here, by electrical energy. So let me show you a quick video of that happening. All right, so this is a hydrogen gas that has been put in a discharge tube, an evacuated tube, and then it was just like turned on like any regular lamp, okay? And what this guy is going to do is that he's going to then put a diffraction grating on this discharge tube. So watch what happens. So he put a diffraction grating over the camera and looking at the hydrogen. And you can see those distinct lines. And that's super duper important. So what's happening? The hydrogen bonds are being broken. We added the energy to it. So the hydrogen atoms are excited now. They have extra energy, woohoo! And they're going to release a photon when they go back down to a lower level. Okay, so that produced the emission spectrum, and that's what we saw, that diffraction grating on that video. All right, that's the emission spectrum. If you go back, you can see those different lines coming out of the hydrogen. Okay, so there were some bright lines if we pause long enough to look at it, they have continuous radiation there, the bright lines, the bands. And they are provided by specific emitting substances as it loses energy and returns back to ground state. So this is hydrogen, all right? So if we had a spectrometer with that diffraction grating, we can look at the ruler with those lines, and we would see there's like a violet line at 410, a bluish line at 434 nanometers, a teal line at 486 nanometers, and then a red line at 656 nanometers. And this is hydrogen's distinct footprint, if you will, all right? That there's no other element will have that exact wavelengths, okay? So that's unique for hydrogen. So then what? Well, Bohr came around, all right, and he explained what's going on here. He explained why the emission spectrum of hydrogen consists of those specific wavelengths. Therefore, because we could calculate it, those exact frequencies that agreed with the experimental data. So here's the hydrogen I just showed you. The ground state is the lowest energy state of an atom. So if you think about it, if I had that discharge tube and I don't turn it on, you don't see anything. It looks like an empty tube, okay? So when do you start seeing that color is when you flip the switch, add energy to that discharge tube, enough energy that will break the hydrogen-hydrogen bond, and now the electrons are, in a sense, free to be excited, woohoo, jump to a higher level, and then as they come down, they have an exact wavelength. So what does that mean? If they have an exact wavelength, they have an exact frequency. If they have an exact frequency, then they must have an exact energy. Did you write that down? That's really important. I'd write that down if I were you. So what am I saying? That these exact wavelengths can be calculated into finding exact frequencies. Hey, what's new? C over lambda. Yes, that. All right, and once you find your nu, you can find your exact energy. Yes, E equals H nu. So how does that help? Well, let's find out. Let's turn the page. So you might have seen these rings that represents the Bohr model, okay? So here's your inner ring, here's your next ring, here's your next ring. So what's happened? I have some electrons maybe at E1. Then what? You give them energy. You add electricity to them. Woohoo! They get excited. Woohoo! And when they do, they jump to an outer level. Okay, that's absorbing energy. But now what? They're going to release energy and they're going to go back down. Maybe they're going back down to that spot. Maybe they're going to go back down to that spot. So why are there 4 lines? Well, there must be 4 jumps of the hydrogen, at least that we can see. Hint, hint. All right. So that when these electrons are going back down, that's an exact jump. And from this ring to E1 is an exact jump. So those are exact energy. So let's say E2 minus E1 is an exact energy. E3 minus E1 is an exact energy. Okay, so we can see that here and we can see that here. So my point is those exact energies from the falling electrons can be then calculated to exact frequencies, which then can be calculated to exact, yes, wavelengths. And that's what these 4 numbers represent. Those are your 4 jumps for hydrogen that's in the visible spectrum. That's an important point. That's in the visible spectrum, okay? So once again, because they have definite wavelength, they have definite frequency, therefore the clincher is they have exact energies, all right? So now what? Niels Bohr was looking at this and he came up then with the idea of this. Now actually, if you go back, Rutherford came up with the solar system model of these rings and he called them orbits. All right. Well, Niels Bohr added to Rutherford's model and said they're not just any old orbits. All right. They have exact energy orbits. So this is a defined energy level. This is a defined energy level. Okay. So that's how Bohr improved on the solar system model of Rutherford. Okay, so let me scroll back down to him. So these electron orbits are the energy levels. They can circle the nucleus in only allowed paths or orbits at certain energies. The energy electron is greater when it's further from the nucleus. Okay, the atom achieves the ground state when the atom occupies the closest possible position around the nucleus. Hopefully that makes sense. And the electromagnetic radiation that is emitted when electrons move closer to the nucleus are called photons. That is the energy that is released when the electron goes back down. So let's kind of go back up here again. So here it is. The energy of the photon is the energy that is released, so it goes back down to ground state, wherever the ground state was. Okay, it doesn't have to be E1, by the way. Okay, ground state might have been E2. We don't know. So, but the idea is that the energy of the photon is that jumped difference. Okay, so that's Niels Bohr's contribution. Okay, so the energy of atoms are fixed, definite quantities. We call them quantum. All right, quantum mechanics. Quantum is a definite quantity. Energy transitions occur only in exact amounts of energy. Electrons only lose energy when they go to lower state. Now, my analogy that I like to do in person, and maybe I can show it to you next time I see you, is if I am standing on the ground, I'm at the most stable state, right? I'm on the ground. You might put it back with physics and say I'm at the lowest potential energy. I'm closest to the ground, okay? But you know me, I love my chocolate. So what happens when I grab some chocolate? Oh my goodness, I've gained energy. I got really, really excited. So what am I going to do? Woohoo! I'm going to jump to the chair because I am so excited. Okay, so now I'm at a higher energy level. I'm on the chair. I'm not as stable either. All right, so I have a choice. I can either gain more energy and go jump on my desk, or I can lose energy. So why don't I just lose some energy, all right? So I'm going to emit a photon, so I'm going to fling the wrapper out, all right? And I'm going to go down to back to the ground. Now, can I jump halfway between the ground and the chair? No, I can't float in space, sorry. I'm either on the chair or I'm on the ground, and that's it. All right, so that's what we mean by the energy transition occurs in jumps of discrete or exact amount of energy. I can't be anywhere in between, okay? So that's an exact amount of energy. That is a quantum of energy, okay? And so these numbers here, then what? Those represent the exact amount of energy. Now, this next picture on the next page is really going to show that to you. I really like this picture. To me, it shows an awful lot. Now, one thing to note, it says electron transitions for the what? Hydrogen atom. All right. Go ahead and highlight the word hydrogen atom. So remember what I said? You could, take these and you could jump up and down, right? So this could be ground state. N equals 2 could be ground state. N equals 3 could be ground state. Okay, and look what happens here. Do you see these lines right here? I tried to color coordinate those as well. So when we looked at that spectrum on the other page where we had the nanometers of 410 and so on, that's your violet. Here's your 410 right here. All right, here's your next one. Here's your green, that teal color. Here's the red color. So that red is being emitted when I jump, well, not me, but electrons go from the third energy level and jump down to the second energy level. So how they do that, they release a photon. All right, they release a photon that has an exact energy, that has an exact frequency, therefore has an exact wavelength, and we can look at that in our spectrometer. All right, but now what do you notice? To me, this makes so much sense, because if I look at violet, blue, teal, and red, my violet is the biggest jump. I'm going from N equals 6 to N equals 2. That's my biggest jump. That's my biggest energy. So why does violet have the greatest energy? Because it's the biggest jump. All right. Why does red have the lowest energy? Because it has the shortest jump. Now, do you remember what I told you earlier? Those 4 lines represents the 4 lines that we can see. Are those the only lines available? No. All right. Actually, this line right here would represent infrared as well. I'm sorry, UV. I made a mistake. That's UV. Notice how it's next to violet, and notice how it has even a greater energy than violet. It's just out of the visible spectrum. So this, if I want to jump from anything to the third energy level, that would be your infrared range. Okay, so I want to jot that down. And then this Lyman series, when you jump down to N equals 1, those are huge jumps. All right, that's your UV. Okay, that's your UV. Now think about it. The sun. What 3 forms of energy does the sun contain? Infrared, visible, and UV. Infrared is heat, visible is visible, and UV gives you sunburn. All right. Why do you think that is? How come we don't get X-rays necessarily? All right. We're talking about hydrogen, aren't we? And so the hydrogen in the sun is being excited. All right, and those are your 3 forms of energy that arrive to the Earth. Okay, so you have IR, visible, and UV. Okay, so what's the thing you need to understand? As frequency goes up, wavelength goes down, and then you have more energy. As frequency goes down and wavelength goes up, you have less energy because you have less jumps. Okay, so hopefully you got this figured out. Which has more energy? Violet does. Why? Let's look. Oops, scroll back up again. Because this is your longest jump. All right. Which is your lowest energy? Red. Now, what about these 3? IR, visible, UV. Which one has the biggest jump? Which one takes more energy to go from the top to the bottom? It's definitely the UV, I should say this, which one releases more energy. That makes a lot more sense to go from the top to the bottom. Okay, so there you go. All right, and so I go, see, chemistry does make sense. I love it. So that is the end of section 7.3. Don't wait to be great. We'll see you next time. Bye-bye.